We are back for part B. So chapter 12, section 1. All right, so we're now, the next couple questions are much more interesting to me and much more germane to you, to your future studies, as well as germane to your tests. But let me go ahead and state from the onset. So the example that we're going to be given is, how do we find the vector valued function that models a curve, right? So instead of, the previous question was, we were given the vector valued function, and then we were asked to trace the curve, but now we're actually going to be seeking the vector valued function that models the curve. So let me show you the game plan here. So this R of t, this is what we're looking for, right? That's going to be the goal. Just let me restate that as we've already seen, the x models the f of t component of I, y the g of t component, z the h of t component. So what I'm going to do is I'm going to show you how easy it is, right? This game becomes really easy to find R of t if you have your equation in parametric form, right? Obviously, looking forward, example 3, that is not in parametric form. But let me just show you how easy it is if it is in parametric form. Ready? So assume that example 3 asked us to find the vector valued function, and this is the description that they gave us. Well, watch how easy this becomes. So the answer, R of t, would be, let me go ahead and write my I, J, and K. The answer is quite simply, we just get to plug in. So 2 plus t, and then we will plug in for the y, and finally we'll plug in for the k. So if you're given the parametric description of your curve, then it is very simple to go from parametric form to vector valued function. You're just simply plugging in to the components. So what is the game plan? Let's now jump to example 3. The game plan is to take this rectangular equation and get it into parametric form. All right, so let's start. So how do we get y equals x squared plus 1 into parametric form? So first, let's go ahead and notice that we don't have a z variable. So in this case, we are in a plane. So we only need the x component and the y component. And let's go ahead and begin. Well, please don't make this hard on yourself. Take my advice right here. You have some degrees of freedom here. You can choose, right? Because we need to choose a parameter, t, and we're going to use t. Well, you can choose, whatever you want, but let's, as I said, make things easy on yourself. Just always begin with x equals t. Let that be your first step, right? I get it. There's in some examples it might be more beneficial to do something differently, but please, let's you and I just assume that my first step is going to say, let's define x to be t. So as soon as you define it, you already have your first component. Now, we also need y to be in terms of t, but that's easy, right? If x is now defined as t, I will just plug t in here for x. So therefore, y is going to be equal to and we want to make sure we use parentheses here, t squared plus 1. So you have, at this stage, you have your parametric description. The reason why I use the parentheses will become apparent in just a second. So as of now, let's go ahead and form our vector valued function. All right, so plugging in for plugging t in for where x would be. All right, plus, and now if you let me make a mistake, but I'll make a mistake using the stylus. Let's assume that a student just plugged in t squared plus 1 like this. Well, in that case, I don't know if this t squared, it's not apparent what it is that you're doing here. You want to make it apparent that this t squared plus 1 is all part of this j component. And we can do that quite simply just by using parentheses. So t squared plus 1. And there you have it. There's your vector valued function. Now, the next step would be to write any domain restrictions for t. Right. So our first step is to get it into a parametric form. The second step would be from parametric form to go ahead and form your vector valued function. At this stage, we can't stop here because just imagine if this is the product that you give to your customer. The customer needs to know if there's any domain restrictions here for t, right? If t cannot be greater than 3, then you need to state that. But let's go ahead and look at each component. So can you and I agree that the domain of the first component is negative infinity to positive infinity? We'll look right here. We'll do it this way. So the domain for the first component is negative infinity to positive infinity. What about the second component? Well, the domain is also negative infinity to positive infinity. So there's no domain restrictions. T is free. You know, you could state t is all real numbers. You could also write it like this if this is more beneficial or helpful to you. But we just want to make sure that we tell our customer what it is that he or she is allowed to plug in for t. Okay? Let's go to another problem like this. It'll be a little bit harder, and there will be some domain restrictions, but the process is the same. Ready? Let me read. So it says that we're interested in sketching the curve C, but I'm not really interested in that part. I'm interested in getting my vector valued function. So let me continue to read. Sketch the space curve C represented. Now this is an intersection of two different curves. So we have a semi-ellipsoid, which is modeled here, and that curve is intersecting with a parabolic cylinder defined as y equals x squared. I'm gonna show you the geometry of what that means really quickly. Again, I'm not interested in the actual graphing part, but I just want you to see what's happening. So you can see the ellipsoid, and you can see the parabolic cylinder. So when these two intersect, the points that they have in common are traced out by this curve right here. Okay? So that's the intersection of them. Now, what we're looking for Okay, so we want an r of t. Are you with me? Are you still awake? We want an r of t where if I plug in a t value, it'll plot to every single point on this curve, this intersecting curve, right? It would trace it. We want an r of t that'll do that. That's the goal. So let's start. Remember, first step, parametric description. Then we'll go from there. So we are in 3 dimensions. We're in space. So we're gonna need an x equals, y equals, and we're gonna need a z equals. All right. As I said in the last problem, please make things easy on yourself. Let's just choose x equals t. There we go. So that we start there. Now, once we've defined x to be t, all right, well, look, we can go to either one of these equations, right? Doesn't matter which equation we go to. But can't you see that if I plug t here for this parabolic cylinder, that I can now form y as a function of t? So I could have plugged t over here for x, but that's not going to help me solve for y. Agreed? Because I would still have y variables and z variables. But if I plug t in for x here, then now I have y is equal to t squared. All right, we're almost there. We have the first 2 components. Now, from here, we're going to have to go to our first equation. And what we're going to do is we're going to plug t in for x, and we're going to plug t squared in for y. Be careful with that y because it's y squared, right? So that's going to be t squared squared. So be careful there. So that's what I'm going to do right now. So this ends up being t squared over 12 plus, well, if I square t squared, that's going to be t to the power of 4 over 24 plus z squared over 4 and is equal to 1. All right, let's take a quick glance at this restriction that z must be greater than or equal to 0. We'll come back to that in just a second. Ready? So what's the goal? I want to write z as a function of t. So my goal right now is to solve for z. All right, so I'm going to do this. This is just baby algebra, but I'm going to go ahead and I'm going to write it out for you so you have good notes. So I'm going to first get z squared over 4 by itself. All right, so let's get z on one side of the equation and everything else on the other side of the equation. So that ends up being 1 minus t squared over 12 minus t to the 4th over 24. Okay. At this stage, I'm going to go ahead and combine these I want to combine these into one fraction. You could also distribute a 4 if you want to, but I'm going to go ahead and combine them. So let me do that right now. So that would give me z squared over 4 is equal to LCD of 24, so that's going to be 24 minus 2t squared minus t to the 4th over 24. All right. So I am gonna multiply by 4 in just a second, but I'm gonna go ahead and factor this. This is just my game plan. You may have done it slightly differently, and that's okay. But if I go ahead and factor that numerator, I would have 6 plus t squared multiplied by 4 minus t squared over 24. All right, so really quickly, in class, maybe you're like me. In class, sometimes if I'm watching, I'm in college, I'm watching my professor, and my professor does something, or, like here to here or here to here, and I'm stuck at that step, but my professor's keeps moving. What I need you to realize is I don't want you to make some of the mistakes that I made. I would have to be on guard because I would get stuck on this step, and instead of listening to what the professor's saying as the professor finishes the problem, I'm trying to figure out how the professor went from this step to this step. But wait a minute. You're in Calculus 3. If I'm in Calculus 3, then I should be able to trust that if I sit down, give myself a few minutes, I'll figure out how to do some of this baby algebra, baby, arithmetic that we're doing. I need to just trust that, put a placeholder there and come back to it, right? So just say, okay, here, put a pen there, and then let's stay on the ride. Let's follow the professor through the rest of the problem. You are in a little bit of luck because you could pause the video if you wanted to. But at this stage, let's go ahead and multiply by 4. And now we got z squared by itself. And in just a second, I'm gonna take the square root so that I have z, so that I can solve for z. So let me not talk and write at the same time, because disaster may come. All right, and 4 goes into 4 once, 4 goes into 24 6 times. So nothing left to do except take the square root of both sides. So z is equal to plus or minus the square root of 6 plus t squared times 4 minus t squared over 6. And now, we had glanced at that restriction on z before we started this. Remember, z must be greater than or equal to 0. So that tells me which one of these to choose, right? Because if that restriction wasn't there, then I could write positive z or the negative z. But because of this domain restriction, I'm going to go with the positive version of that square root. So now let me go ahead and write z. So z is the positive square root. 6 plus t squared, 4 minus t squared over 6. All right. Well, beautiful. So I now have a parametric description of this curve. So I can quickly go to my vector valued function. R of t is going to be equal to t in the I direction plus t squared in the j direction plus, let's see if I have enough space, plus the square root of 6 plus t squared times 4 minus t squared over 6 in the k direction. Okay. So this vector valued function would trace out this curve perfectly, this intersecting curve. But what you have not given me, the domain restrictions of t. What is my limitations? Can t equal anything, or are there limits? So let me see if I have room on the next page. I don't, so let me create some space here. And now the last step of this problem is to make sure that I list the domain of t. So ready? Let's go ahead and go component by component. So let's start with the first component. Well, I have no domain restrictions there, negative infinity to positive infinity. Let's go to the second component. I have no domain restrictions there. And now we'll go to the third component. And let's see if we have any domain restrictions in the third component. Well, the third component, we have a square root. So we know that this radicand has to be greater than or equal to 0. So let me write it. I'm going to go ahead and take the radicand, 6 plus t squared times 4 minus t squared over 6, and let's form an inequality that must be greater than or equal to 0. Okay. So how do you solve for t? Well, so pay attention to me, because I'm gonna show you some things that you can do that makes stuff like this a little bit easier. So first off, I can multiply both sides of this inequality by 6. Why? Why can I do that? Why can I just get rid of the 6 by multiplying both sides by 6? Well, because this 6 is not going to contribute because we're going to see if we can form a situation where it's equal to 0. And the only thing that we're worried about is the factors that have t in it, right? If this 6, if I make this, in other words, I'll say that one more time. If I can make this factor 0, then what does it matter if I divide by 6? 0 divided by 6 is still 0. So let me go ahead and get rid of that 6. That leaves me with 6 plus t squared times 4 minus t squared greater than or equal to 0. And now let's slow down for a second. So let's make sure we understand. Greater than or equal to 0. So this side over here can be greater than or equal to 0. So we're worried about negative numbers, right? So can you and I agree really quickly? Let's look at this 6 plus t squared. Is there any possible way that you can make 6 plus t squared a negative number? Right? No. I mean, no matter what, if you choose -1, you're going to square it. It's going to become a positive, right? So this, we're good to go here. This is not going to cause any domain restrictions because this is always going to be true. This will always be greater than or equal to 0. If there's this right here, this factor is going to be the problematic factor. So we don't have to worry about the first factor. It's just 4 minus t squared has to be greater than or equal to 0. And ready, let's solve. Let's solve for t. So I'll go ahead and bring the t squared over here, take the square root of both sides. So that's going to be t is, if I take the square root of 4, is 2, so that's plus or minus 2. All right, ready? So you just figured it out. T must be between -2 and +2. So here's the vector valued function for your customer, and the customer turns to you and says, what are the restrictions on t, and now you tell the customer t is between -2 and +2, and you're all done. All right, so we have defined, so we're going to conclude. So we've defined vector valued functions. Now that we have functions, we want to know how to do the calculus of functions, right? So in the next section, we're going to learn we're going to start with limits, and then we're going to build to derivatives of these vector valued functions, and I'll see you there.